Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to learn how to draw Lewis structures for polyatomic systems, where these are essentially going to be molecules with 3 or more atoms. So this is going to be a little bit of a tricky idea, which takes a lot of practice to just really get comfortable with and until you know what typical molecular structures look like. So we can do this using 5 key steps. So the first thing we need to do before we build a structure is we need to know how many electrons are going to be involved in making our structure. So we can do this by first identifying all of the atoms present and then counting up the total number of valence electrons involved, because these are going to be the electrons that can be potentially shared amongst all of the atoms forming our general structure. However, our system may be charged. And if we have a charged molecule, then this means we either have a couple extra electrons, in which case we have a negative charge, and then subtracting a negative should give us a larger number of electrons, or we could have a positive charge, at which point we'll be short a few electrons, which again, this subtracting electrons helps guarantee. Then the real key tricky step is trying to generate a skeletal structure. So when I'm talking about a skeletal structure, this is going to include only the atoms and the atoms present connected by single bonds. So we're going to ignore any lone pairs, any double bonds, any of that. So this takes a little bit of practice, but a good general rule is we start with the least electronegative atoms. So if you have any metal ions, you'll start with these. But most of the time, we're starting with carbon. And then we're going to add progressively less electronegative atoms. So after the carbon, then we have nitrogen, then oxygen, and then we finish with our halides and hydrogen. Hydrogen is a little bit of the anomaly because hydrogen only makes a single bond. It's a good atom to essentially sneak in the places where no one else will go. And in general, we're going to try and want to make sure that our atoms won't violate the octet rule, which means that none of our atoms should have more than 4 bonds. Additionally, and that hydrogen only has a single bond. And additionally, good structures tend to have a certain degree of symmetry. So this is another way of saying that we want things to be kind of evenly spread out amongst the molecule. So having a long stretched out system, usually not so good. Next up, once we have all of our atoms set up, we're going to need to start including all of our electrons. So we're going to start including them as lone pairs. So this is where you first need to figure out exactly how many electrons are used up in bonds of your skeleton structure. And then you can simply put the rest around your system one by one until we've run out of our total number of valence electrons. So here you're going to want to start around your most electronegative atoms. So start with your halides, then oxygen, then nitrogen. And hopefully you've run out of them all by the time you hit carbon. If you haven't, go ahead and revisit your skeleton structure. Now, at this point, and again, while you do this, you want to make sure that nobody exceeds the octet rule. However, at this point, if you run out of electrons and not everybody has an octet, then you're going to need to start making double bonds. So you can do this by essentially taking electrons from one atom and then moving them to the bond to help support another molecule that hasn't completed any octets. After this, make sure that all of your electrons have been used and you don't have your counts wrong, and then all atoms have filled octets. If they don't, you may want to revisit, make sure you have a good skeleton structure, make sure that you've spread out all of your electrons to make bonds that you can. So this, again, a little bit vague, so let's go ahead and get into the details. First is some good guidelines for building those skeleton structures. First thing you want to know is what number of bonds any given atom tends to form. So if I'm working with carbon, carbon has 4 valence electrons, which means that it has exactly as many electrons as it can make bonds. So in order to complete the octet rule, it tends to want to have 4 bonds. Now this can take any number of forms. It can either have 4 single bonds or 2 double bonds, because each double bond counts as 2 bonds. Or it can have 1 single bond and a triple bond, or 2 single bonds and a double bond. Regardless, they always add up to 4 bonds, And most of the time, carbon doesn't like to have any lone pairs. So this can be a good guideline to make sure your Lewis structures follow. If they don't, you have to watch out, but you may have the ability to form double bonds to help save the day. But make sure you're going to have an electronegative atom with the extra electrons to make that possible. Next up is nitrogen. Nitrogen tends to like to make 3 bonds and has 1 lone pair. But again, worth noting, these 3 bonds can be doubles, singles, or triples, or any combination thereof. Most likely a double and a single. Then we go to oxygen, which can only form 2 bonds. So either a single or a double, and has 2 lone pairs. Halogens tend to have 1 bond and 3 lone pairs. So these are, again, those pairs of electrons that haven't gone into forming a bond. And hydrogen only forms 1 bond, but because it only wants 2 electrons, has no lone pairs. Then we get in kind of the oddballs like beryllium, which only has 2 valence electrons, so only tends to form 2 bonds and no lone pairs, as well as boron with 3 valence electrons, tends to only form 3 bonds with no lone pairs. And we'll talk about these 2 a little bit later, as they tend to violate the octet rule, and that's just fine. So let's go ahead and try and use these general rules to build some sample structures. And we'll start with some species we've seen before. So how about acetylene? So C2H2, only 4 atoms, should theoretically be easy, but we'll see how that goes. So the first step is to figure out exactly how many electrons I'm working with. So I have 2 carbon atoms, each have 4 valence electrons, and 2 hydrogen atoms, each have 1 valence electron. So I add these together and I've got 10 electrons to work with. All right, seems pretty good. From here, I can write a skeleton structure. So a good place to start is 2 carbon atoms. And then to maintain symmetry, if I put a hydrogen atom on this side, I'm probably going to want to put a hydrogen atom on the other. Things tend to get a little bit messy if I try and put 2 hydrogen atoms on the same side. Now that uses up all my atoms, so everything else has to be lone pair electrons. So I've got 1, 2, 3 bonds, which gives me 6 electrons, 2 electrons in each bond. So out of 10 electrons starting, I use up 6. I've got 4 electrons left over. So I'll put 2 around one carbon and 2 around the other carbon. Unfortunately, this carbon now only has 6 electrons. 1, 2, 3, 4, 5, 6. Same thing with the second carbon. 1, 2, 3, 4, 5, 6. So in order to try and make sure that they maintain both these carbons maintain the octet rule, I'm going to move these 2 electrons to this double bond. So that way, this carbon will have 6 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8. This one will only have 6. So I'll move this lone pair to form a triple bond so that everybody will have 8. Both the carbons have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And my hydrogens are satisfied with 2 electrons each. 1, 2. Now let's go ahead and double check, make sure everybody's happy. So I should have a total of 10 electrons, and we can count through 1, 2, 3, 4, 5 bonds, each with 2 electrons each, gives me 10 total electrons. So this should be a pretty good structure. Now let's deal with something a little messier. And by a little, I mean much. Let's deal with, this should be acetic acid, or acetate. So acetate is an ionic form where it's got 2 carbons, 3 protons, and 2 oxygen atoms and a negative charge. So counting up the valence electrons can be a little bit trickier here. I still have 2 carbon atoms with 4 electrons each. Now I've got 3 hydrogen atoms with 1 electron each, and 2 oxygen atoms with 6 electrons each. But I now have this negative charge, which gives me an extra electron. So I add up all these numbers and I'll have 24 total electrons. So here we can go ahead and start writing up a reasonable skeleton structure. So this is a little bit messy. So we go ahead and start with our 2 carbon atoms. Now this time, to maintain a certain degree of stability, I'm going to put all of the hydrogen atoms on one end and all of the oxygen atoms on another. So this generates an oxy species. So it can be fairly stable. Again, it is worth noting, carbon atoms very rarely like to have more than 2 oxygen atoms each. So doing this, I first want to count up how many electrons I've used. So I have 1, 2, 3, 4, 5, 6 bonds. So that gives me 12 electrons I've used so far. So I've got 12 more electrons to add. So I'll go ahead and add them around, starting with my most electronegative ions. So 1, 2, 3, 4, 5, 6 on this oxygen atom, and then 6 on the other oxygen atom. So I've now used up all 24 of my electrons. Unfortunately, I came out 2 electrons short, as carbon is missing electrons. So I can do this by doing the same thing I did last time. I've got extra lone pair electrons around this oxygen, so I'll move one of these lone pairs to form a double bond. And now I should have a pretty good structure. All of this carbon atom has 4 bonds. This carbon atom has 4 bonds. This oxygen has 2 bonds and 2 lone pairs, so we're good. This oxygen atom has 1 bond and 3 lone pairs, which still satisfies the octet rule as 1, 2, 3, 4, 5, 6, 7, 8. So I still should be fine. And we can double check and make sure we still have our 24 electrons. So we should be good. However, it turns out when you're working with acetic acid, there's multiple different structures we can generate. We have the one we did generate, and you can have a very similar structure where it has the same bonds, but I've changed which oxygen gets the double bond. We can also split up the oxygen atoms onto different carbons. It is worth noting that this form still doesn't have any symmetry, even if I have an equal number of oxygen atoms on each carbon. We can also try and move a hydrogen atom onto the same carbon atom as the 2 oxygens, at which point we do have a clue that this one might not be right because we haven't satisfied the octet rule for one of our carbons. We also can put an oxygen atom in the middle. This one also looks a little suspicious, but turns out everybody has enough, has satisfied the octet rule. So we should be okay. And then finally, we can go ahead and again spread the hydrogen atoms out and move around our bonds. Now, not all of these structures are going to be possible, but we need a good way to try and evaluate how accurate each of these structures might be. And so we're going to do that next time, as we're going to use formal charge as a way to evaluate how happy each of these atoms are in our proposed structures. And this will help determine which of these structures are going to be more likely to occur. So next time, we'll go ahead and look at molecular stability. Until then, take care.